Good morning, students. Today we'll be learning about polarization. Later we will be seeing the Fazan's rule. Please understand the polarization first of all very nicely to understand the Fazan's rule better. Okay? So, see, when we talk about that bonding to be a covalent or a ionic bonding, we just assume it to be 100% covalent or 100% ionic. But this not may be the case. In most of the cases what we have seen is that most of them are a mixture of both. That is, suppose a bonding is there where you are finding 80% of the covalent character, okay, 20% of the ionic character. You say that bonding to be covalent, of course, okay. Now, suppose another instance where you find 75% of the ionic character in a bond and 25% of the covalent character in that particular bond only. So that bond has to be called as, of course, ionic bonding. Okay. So in that way. Also, students, you must understand the concept of cationic and anionic radii, which you have learned in the third chapter. See, I'll tell you shortly about that. See, in the case of cation formation, what we have seen in the context of that ionic radii, we have seen that when we compare Na plus and Na, Na is a neutral atom where you will be having the same number of protons and electrons. That is, number of protons is 11, number of electrons is also 11. Okay, but in the case of Na plus, number of protons are 11, but number of electrons is only 10. So we can say that in the cases of cations, number of electrons is less than number of protons. And we know that the nucleus with the protons are holding the electrons towards itself. So what we can say is the nucleus in the case of cation will be holding the electrons, less number of electrons as compared to the neutral atom, very strongly towards them. The nucleus of the cation will be holding its own electrons tightly towards itself. In the case of cationic radii, that has to be kept in your mind because that is the base where you learn the other things. Another thing which you have to be very clear in your mind is that about the anion radii. What is that? If we compare anion radii with a neutral atom, anions are the ones where you have extra electrons. For example, Cl is a neutral atom where you have number of protons 17, number of electrons also 17. So in that case, 17 protons are holding 17 electrons. But in the case of Cl minus ion, where you can see number of protons to be 17, but number of electrons has increased, that is 18. So now 17 protons are holding 18 electrons. So that holding must be little less. So I can say that the electrons are not held very tightly towards the nucleus. It's of course holded, but it's not very tight towards the nucleus. So here what happens when we have two oppositely charged ions, of course of unequal size, and both approaches each other, the ion which is smaller in size, that is the cation, will attract the outermost electrons of the anion because electron cloud of the anion is not tightly held towards the nucleus of its own. So that electron cloud can be distorted. Okay, and of course this will also repel its nuclear charge, but it will attract the electrons, outermost electron cloud. So such is the case what you can see in the picture. The X plus cation and what was earlier the Y minus anion which is shown was in circular shape, okay, as normal when it was not distorted. But as both approaches towards each other, the cation influences the electron cloud which is not so held tightly towards the nucleus, and that gets distorted in this way towards the cation. This distortion is actually the reason of polarization. The distortion is actually done by cation only because its size is smaller, and it can quickly distort the anion cloud. So the anion cloud now is not symmetrical as it was before. It becomes elongated towards the cation. The ability of the cation to polarize this nearby anion, that is known as polarizing power. And the tendency of an anion to get distorted or deformed or polarized by the cation is called its polarizability. Okay. Now also you must understand that anion tries to again deform the electron cloud of this cation. But the influence is not much because cation's electron cloud is already strongly attracted towards the nucleus. So the influence is not much, and we are not considering it also. Only we are considering the cation's influence on the anion. Anion's electron cloud is being distorted. Okay. And you also have to understand that due to this distortion, what happens? Due to this distortion, covalent character is going to increase. Covalent character is increased. Ionic character is decreased. Why? Because when it is circular in shape, when we draw it in circular shape, that means that it's not distorted. Not distorted, that is, they are in their own their own ionic forms, so they can form the ionic bonding quite easily. But when it gets distorted, then you must understand that the covalent character has been increased. Okay, so this is through the image. I'll also show you another image where you'll see slowly the anion is going into the cloud of the cation. So what does that mean? See, we have seen the covalent bonding where we have seen that sharing of electrons. The electron cloud was merged for cation and the anion. Then only there was a rise of covalent bonding, right? So when there is a merge of electron cloud, we must understand that there is covalent bonding. And when it is a normal circular form, then it is ionic bonding. So let us go for the next image now. Next image is in this way. You just see cations and anions were in this way. So this is ionic bonding. Okay, this is ionic bonding. Now slowly what happens? The anion electron cloud is pulled towards the cation. Now see, merging happens, and merging, mutual sharing of electrons, we have seen for covalent bonding only. So polarization gradually increases in this way, and thus what happens is covalent character increases. Now we also have to understand about a factor which we call it as phi. Phi is nothing but ionic potential, ionization potential. Okay, this is not ionization energy, okay, or enthalpy. It is ionization potential. Please understand that it's different. Now phi is the calculated. Phi gives us an idea of how able is the cation to deform the anion. So basically we can say that the polarizing power of the cation is judged by this phi. So phi equals to the cation charge divided by the cation's radii. It's very simple. Okay. So whenever we see that cation charge is more or cation radius is less, then we can say that the phi value is more. Now, phi value is more means covalent character is also more. Please understand that properly. Okay. Now we see that from in a period what happens. In a period we see from left to right when we travel, when we move from one element to another, we see that there is a increase in the number of charge and the cationic radii also decreases. For example, I take an example, Na plus and Mg2 plus. So this is left to right, the third period. See, the charge is increased, isn't it? More when we go, we find Al3 plus also. Okay, so the charge is increasing, and so we also know that atomic radii is decreasing. So in that way, we can say from here to there, phi value is increasing, phi value increases, So we can say that covalent character increases. So covalent character will also increase. Hope you have understood that part, and next we go for the next part. Okay, here you can see the Fajans rules. We have the Fajans rules, this all the first factor with us. Okay, that is, the first factor is, there we have found phi. Phi is equals to the cation charge plus the divided by the cation radii, right? Now we find it through cation radii, the first factor. Now, see, when we take the same charges of a cation with different radii, then what happens? This is the example what I have shown it in the image. First of all, understand that we have taken the example of the second group. Second group, we have beryllium, we have magnesium, calcium, strontium and barium. Okay. Now, ionic radii in picometers is given here in the numericals: 31, 65, 99, 113, 135. Okay. So it is increasing. And what we are seeing is the covalent character is increasing in this way. As we know that down the group, what happens? Down the group, the cation radii will increase. Okay. But we have just seen that cation radii was in the denominator. So it has to be decreased so that the phi value is more for covalent character. So down the group, the size increases, means upward the group, the size is less, of course. So it gives us the phi value more. So here the phi value is more, and so the covalent character is also more. How we can just justify with the experiments is that when we take chlorides of all of them, like beryllium chloride, magnesium chloride, calcium chloride, strontium chloride and barium chloride, we see that for beryllium chloride, the melting point comes as 405 degrees centigrade. For magnesium, this is for beryllium chloride. Okay, for magnesium chloride, it comes as, this is 712 degrees centigrade. Okay, so what we can see? We can see that here the covalent character is more. That means the melting point is less. Here it is more. Because we also know that in case of ionic bonding, the melting point is more, and in the case of covalent bonding, the melting point is less. So we can see that as the covalent character increases, that means we can understand that for beryllium it is having more covalent character, so its melting point is less. Okay, in this way. So this is the first point where we can see cation radii. So as the cation radii is less the cation radii, phi value is more, and more the phi value, we know that covalent character is going to be more. Okay. Next factor. This is the next factor. What we can see in the next factor? See, fluoride, chloride, bromide and iodide. Okay. So we can see the radii of ions now. Anions. There we have seen the cation. Now we will see the anion. Now see the ionic radii in picometers: 136, 181, 195, 216. Okay. Now what happens? When the size of the anion is more, then the outermost shell electrons of the anion is very less tightly hold towards its nucleus, because from the nucleus it is going away far. The outermost electron is going away far. So in that case, its hold will also be less. Now when its hold is less, quickly the cation can deform it and polarization happens. So phi value is more, covalent character is more. This is what is happening. Okay. So in this case, the covalent character is increasing. Here we are showing because the size increases, and through experiment we are finding that this is having the less melting point. If we compare calcium chlorides, fluorides, bromides, iodides, then we can say that calcium iodide is having less melting point than which is suppose the one which is before it, calcium bromide. Okay, because in the case of calcium iodide we have the same cation, so not to worry, we have to see the anions only, and we see that iodide anion is larger in size, so deformation happens quickly, and so covalent character is more here. Okay, and before what we have seen that it was in the case of cations, right? So cation, we have seen that anion radii, if it is less, then it is very much able to deform the anions, because in that case its power increases, because it has less number of electrons and radii is small. That means that the outermost shell is now more closer to the nucleus, and so it is tightly held towards the nucleus, so its power is more to attract the anions. This is the case. Okay, next I just discuss about a third factor, uh, of which that is the charge of cations basically we'll discuss, and anions of course is also there. Charge of cation, suppose the charge of cation is Na plus, magnesium 2 plus, and aluminium 3 plus. Now its radii is seen to be 0.95, 0.65 and 0.50. So what we are seeing is charge of the cation is increasing. Okay, when the charge of the cation is increasing, we are seeing that its chlorides are having a melting point of 800 degrees centigrade, 712 degrees centigrade and 180 degrees centigrade. So see, for aluminium Al3 plus, okay, we see very less melting point. That is because it has more covalent character. So that is because the charge is more here. Of course, ionic radii is also less, charge is also more. Similarly, in the case of charge of anion, if so the cation is the same one, okay, similar one, and you compare an anion which has -1 charge and -2 charge. So among that, the more the charge, that is the one which is having -2 charge, that will have a polarizing ability more, because it has to hold more number of electrons, no? It has to hold more number of electrons, so less tightly held electrons can be easily deformed. Concept is very simple. Two things you have to remember, that cation size is smaller, it is better, because when cation size is smaller, the nucleus is able to hold the electrons more tightly, and more tighter electrons towards the nucleus of a cation means better it can attract the electron cloud of anion. But it is reverse in the case of anion. Less tightly held electrons of the outermost shell towards the nucleus will give a better deformation, which is nothing but your covalent character. So anion is getting deformed, cation is actually performing the deformation. Okay, so that you have to understand. Next we go for the next factor. The next factor is, whether the particular atom which is forming a cation is having 8 electrons or 18 electrons in its outermost shell. Suppose for example the alkali metals is taken. Sodium, it has its electronic configuration is 2s2 2p6. Okay, so in this case this radii is 0.95. Copper, the ionic radii is, just see here, the ionic radii is almost same only, 0.96 only. But in the case of copper, when you see the electronic configuration, it is 3s coming into being, 3p and 3d also coming into being. So we have 18 electrons system over here in the outermost shell, and here it is 8 electrons in its outermost shell. Okay, so the one which is having 18 electrons in its outermost shell will have less melting point, 422 degrees centigrade only. That is because it is able to deform the anion quickly. As you have d electrons in this particular atoms, in the transition elements, the d electrons are not having so much of shielding effect. There are poor shielding effects, and thus what happens is these electrons are actually attracted towards the nucleus more. So it can deform the anion easily. Such is not in the case of Na plus. They don't have 8 electrons. They don't have the d electrons. Okay. So the ones which is having 18 electrons will show more covalent character. More covalent character, because it can deform the anions more easily. Okay. Next, it's just for the third period we have just arranged the different elements with the chlorides, and we can see that NaCl is purely covalent, magnesium chloride and also aluminum chloride is with covalent character. Normally we write magnesium chloride as ionic bonding only. We have written, in this chapter before only we have written, right? But it is with covalent character. Now we can understand here. Now silicon, this chloride, phosphorus pentachloride or sulfur chloride is also polar covalent. So they have covalent characters, but they are polar. So there is a minimum of ionic character also. But Cl2 is a purely covalent. So this way we have learned the Fajans rules. I hope you have understood it. I'll surely ask you a few questions. Try to answer those. Okay. Good day, everybody.